smoke that had been coming out from the air conditioning vents, and he knew that smoke in an aircraft is never a good thing. So he had started thinking about what to do about this. But before he could even finish that thought, flight engineer Barry called out, "Engine failure, engine number 4." The time was now 2040 local time, and this announcement by the flight engineer took the situation to a completely new level. Captain Eric called out, "Okay, engine failure and shutdown checklist please." And flight engineer Barry started executing that checklist, and that included items like putting the thrust lever back to idle, the engine start lever to cut off, but also in British Airways pulling the engine fire handle, right? Not actually putting any of the extinguishers into the engine, but arming them so that they were ready to use in case they would be needed. As soon as the engine failure shutdown checklist was completed for the number 4 engine, Barry shouted out again. This time he said, "Engine failure number 2, 3 has gone. They've all gone." So this means that in a matter of a few minutes, this Boeing 747 had gone from a completely controlled normal flight into a flight where now all 4 engines had simultaneously failed. This is a potential catastrophic situation, and the way that the flight crew handles this from this point on is going to be crucial for how successful they are with recovering it. Captain Moody was stunned by this announcement, and he looked down onto his engine instrumentation, and what he saw was a very confusing picture, because on the Boeing 747-200 at the time there were 2 sets of different engine manufacturer indicators. So there was both Smith instrumentation and General Electric instrumentation, and some of them showed the engine values frozen where they were when the engine failed. Other ones went off the scale, making the picture that he was seeing almost impossible to get your head around. And another thing that made him very confused was that he had actually practiced a quad engine failure, as in 4 engine failure scenario in the simulator a few months earlier. But when they did that, almost all of the lighting in the cockpit disappeared, together with all the instrumentation on the first officer's side and some other system. But in this scenario, it seemed like at least one of the engines and the generator connected to it was still producing power, giving it a completely different sensation than what he had had in the simulator earlier on. And here Captain Moody makes a very important decision, because when he looks down on his primary flight instrumentation, he realizes that his speed is starting to tick down. Something that you would expect from an aircraft maintaining 37,000 feet without any engine power. And he also realizes that because he still has some electrical power coming from one of the generators, the autopilot is still working. So he puts the aircraft into a shallow descent, just enough to maintain the airspeed. So he is now focusing on flying the aircraft, making sure that the aircraft doesn't go into a stall and that he has complete control over it. He also initiates a left-hand turn back north again. Okay? Because remember, they have passed the city of Jakarta a few minutes earlier, and they're now out of the sea. If he makes a left-hand turn, he will start heading back towards land and towards a potential airport. He also tells the first officer, Roger, to please send out a mayday call. So at time 20:44, this is 4 minutes after they started seeing the first lights in the cockpit, the following call is made to Jakarta control. Jakarta, Jakarta, Mayday, Mayday, Speedbird 9, we've lost all 4 engines. We're leaving flight level 370. Initially, air traffic control didn't fully understand this message. They thought that they heard that they had lost engine number 4, which is very different from having lost all 4 engines. But that kind of miscommunication kind of makes sense when you think about the likelihood of hearing that an aircraft has lost all 4 engines. That just doesn't happen.
The engineer and myself went through the first checklist, and I detailed the co-pilot to send out the Mayday call, which is when he had the first problems, because there was so much static around the aircraft for obvious reasons that his communications were intelligible, and it took a little while to get through to the Jakarta Air Traffic Control, who's English. I mean, we're talking about 1982. You go out that way now, it's not fantastic. But in 82, it was even worse. And he had great trouble getting through to them because it was a non-standard phrase. All 4 engines have failed. If he'd said number 4 engine has failed, they might have understood that. But he said all 4, and eventually it took a Singapore Airlines aeroplane who was about half an hour behind us on the same route to relay to them, no, they have no power going, no power.
What has actually happened here, which I'm guessing most of you have already guessed, is that the aircraft has flown into a layer of high altitude volcanic ash. Volcanic ash is spread from volcano basically in 2 different ways. So you have the main black plume. That's what you're all thinking about when you're thinking about a volcanic eruption, which is mainly pieces of brimstone, ash, lava, stones that are being thrown out on top of the volcano. But then higher up, this gets separated into the finer kind of ash dust. And this tends to be whitish in color. If you've ever seen a satellite photo of a volcanic eruption, you tend to see the black main plume going one way, and then you'll see a slight white cloud going a slightly different way. This whiter cloud tends to be containing smaller particles, down to as small as 1 micrometer, and it can travel hundreds of kilometers away from the main volcano. It can also be included in cloud masses and so on. These particles are electrically charged. That's why you sometimes see these lightning bolts from a volcanic eruption. But this is what caused that St. Elmo's fire that the flight crew saw, and also the lights from inside of the engine. The reason that the weather radar didn't show anything was because the weather radar is not designed to pick up particles as small as the volcanic ash particles are. Remember, volcanic ash can be as small as 1 micrometer, and most of the particles at those altitudes are not much bigger than that. And because of that, the weather radar, which is designed to pick up moisture and droplets, didn't see anything. In order to see things like volcanic ash, you would need a weather radar with a very different wavelength. A smaller wavelength, but the weather radar on board the 747-200 did not have that. Hence, Captain Moody did not see anything on his weather radar, even though he was surrounded by large concentrations of volcanic ash. If someone was trying to create a material that was solely designed to disrupt aircraft systems and be damaging to aircraft, then volcanic ash would be pretty close to the ideal material. Because this type of volcanic ash will not just attack one system, it will basically attack all of the aircraft systems. So the main threat obviously is what it's doing to the engines, because these tiny little particles, if you look at them with your naked eye, it looks kind of like baking powder, right? Or baking flour. But if you use a microscope, you will notice that they tend to be mostly silicates, and these silicates are extremely sharp, making this material very abrasive. So the first thing that will happen to the engines is that the engines are sucking in enormous volumes of air, and that means that it will concentrate the volcanic ash inside of the engine. And this abrasiveness will start to wear down the fan blades, the compressor blades, and the turbine blades, changing the aerodynamic property of these blades, causing things like engine stalls. But as the ash goes further into the engine and into the hot part, the melting point of these silicates is around 1100 degrees Celsius, while the normal working temperature of a jet engine inside of the core can be as high as 1400 degrees Celsius or higher. So this means that these silicates are now melting into glass, and this will get stuck onto the igniters, onto the fuel nozzles, and onto all of the hot parts, the turbine blades and so on, that's coming after the hot part. And this can stifle the engine completely. But on top of that, this high abrasiveness of the volcanic ash will start sandblasting the outer part of the aircraft. So the aircraft's windows, for example, the pitot tubes, the static probes, the angle of attack vanes, all of those can be damaged, causing faulty instrument readings inside of the cockpit. And then the volcanic ash will get its way in through the air conditioning ducts, for example, stopping vanes and valves inside of the air conditioning and being pumped into the aircraft, where it will smell like sulfur, or that acrid smell that Captain Eric Moody felt. Also, it's going to be irritating for eyes, people breathing it in. It's not good for anything. But it also goes into the fuel tanks through the vents, the air vents, where it contaminates the fuel. So all in all, going into a high-level volcanic ash cloud with high concentrations of ash is a very, very bad thing for the aircraft. The flight crew knows nothing about this, so they are now working frantically on trying to restart the engine. And they're discussing whether or not they're going to try to restart engine number 4 as well. Remember the one that they did the engine failure and shutdown checklist for, because they had pulled the fire handle. And if you pull the fire handle, then that engine will not be restarted unless you push